Various recently published articles have prompted me into writing some notes on tribometer dynamics, not least a discussion piece in TLT about improving the repeatability and reproducibility of the full ball test. I'm not entirely sure why anyone would want to do this, bearing in mind that it's a 90-year-old test of somewhat questionable validity. But said discussions did at least prompt me to consider the more general question, why would the results from my machine not correlate with the results from someone else's machine? And perhaps a supplementary question, how does this affect any attempt at big data analysis and the application of AI to tribology? Test machine behavior affects what the contact experiences and thus affects the evolution of friction and wear. Professor Chikos made this point many years ago. Friction, wear and other tribological phenomena are system-dependent responses and are not intrinsic material properties of the components of a given tribological contact. The properties measured in an experiment using any tribological test machine are, by definition, system responses. It follows that the data generated from any properly calibrated test machine must be valid, but only for the response of the material pair in that particular tribo system. Obviously, different systems give obviously different responses. This rather begs the question, how should we compare these different system responses when the dynamics of said test systems have not been defined or analysed? Many test standards define operational parameters, for example, specimen preparation, load, velocity, temperature, and test duration, but fail to mention key system characteristics affecting the system response, such as the stiffness and inertia of the loading system, the rate of acceleration of a motor, the stiffness of the AC or DC drive, or indeed the signal bandwidth and frequency response of sensors and measuring systems. In this talk, I will explore some of the effects of these undefined parameters on various long-established test systems. The data presented will hopefully provide an explanation for why nominally identical test procedures run on different machines with similar test geometries give substantially different results. We know that regardless of the tests we wish to perform and the configuration of machine we have chosen, mass, stiffness, and method of load application all have significant influence on the results produced by a given design of test machine. How significant are these effects? The work illustrated here was carried out by the UK National Physical Laboratory following the results of the Versailles project on advanced materials and standards. The VAMAS interlaboratory tests have produced a factor of 3 in the distribution of reported friction coefficients and an order of magnitude variation in wear coefficients. For the MPL tests, a range of different mechanisms were used to apply nominally the same load on a pin-on-disc machine. Substantial variations in wear rate were generated simply by altering the dynamics of the loading system. More recently, we used one of our standard sliding 4-ball machines to provide a ready platform for comparing pneumatic loading with dead weight loading. Extreme pressure tests were performed by the same operator with a single machine with interchangeable loading systems. Load was calibrated against a load cell inserted between the lower specimen carrier and the machine's spindle, ensuring that the static load with both systems was identical. It therefore seemed reasonable to assume that any change in tribological response could sensibly be attributed to the different loading mechanisms. Multiple tests were run at different loads, establishing that, on average, at nominally identical loads, the wear scar diameter with deadweight loading was approximately 15% larger than with pneumatic loading. This is an example of how the higher stiffness and inertia of the loading system gives rise to higher wear rates. Although there were differences in frictional response with the different loading systems, it's hard to draw any firm conclusions from the data. This is perhaps to be expected with a relatively severe test procedure that only runs for 10 seconds. The original 4-ball machines used direct online starting 4-pole AC motors, which accelerate quite quickly, but not in a controlled fashion. It was never considered necessary to determine how different AC motors might accelerate at the start of a test, or to compare their performances. On startup, these motors jerk themselves into motion, generating self-excited torsional vibration, with, for a short period of time, significant torque reversals. Could variations in this startup behavior have influenced test results and repeatability and reproducibility? The advent of AC vector motors and vector drives allows precise control of speed ramps. This capability has allowed us to investigate the effect of test spindle acceleration on the severity of the 4-ball EP test. The lubricant chosen in this case was Shell Tellus 22, and the ramp time for acceleration to the test speed of 1500 RPM varied between 0.1 and 1 second. Tests were performed at varying loads and spindle accelerations to establish the point of transition between wear and seizure. Data for 2 different acceleration tests, 0.1 seconds and 0.5 seconds, are given here. The faster the acceleration, the more severe the test. Our tests confirmed that spindle acceleration with an electrically and mechanically stiff driving system influences the initial seizure load. So, what would happen with a less stiff drive? In other words, with a motor where the acceleration is affected by the frictional resistance. To investigate this, tests were run with the drive current limit reduced, thus making spindle acceleration more dependent on friction torque resistance. Reducing the available torque from the motor by limiting the drive current results in much slower acceleration of the test spindle and hence a much less severe test. Now, what about reciprocating drive systems? Let's start with voice coil actuators. We do not have to go far. Indeed, we do not have to do any experiments to discover examples of effects of reciprocating drive system stiffness. There is plenty of information readily available for analysis in ASTM standards. In particular, the precision and reproducibility statements and the published data from interlaboratory tests. This example comes from ASTM D7421 of 2011. Standard test method for determining extreme pressure properties of lubricating oils using high frequency linear oscillation test machine. Table 1 gives results for tests run on 3 different oil samples at either 1 mm or 2 mm stroke. Plotting standard deviation gives these graphs. Analysis of the data demonstrates that the shorter the stroke, the greater the standard deviation, and the higher the load, the greater the standard deviation. This is a good example of a system response. In this case, the response of the method of actuation to changes in stroke or resisting force. This is indeed a system response, but it has more to do with the method of actuation than the fundamentals of the tribo contact. We are, in effect, using the tribo contact as a friction brake dynamometer to characterize the performance of the electromagnetic actuator. Tests using a mechanically driven short-stroke reciprocating tribometer showed that such devices consistently produce a larger wear scar than the PCS HFRR instrument. The difference in wear scar size is particularly marked for the low lubricity reference fluid. This arises because of the difference in the method of actuation. The HFFR uses an electromagnetic oscillator, which is a force generating as opposed to a displacement generating device. The resulting stroke length may vary as the frictional resistance of the contact varies, and the control system adjusts the driving force to compensate. These differences do not represent a problem, as the specified test is a comparative test and the result is a simple offset bias, with the mechanically driven reciprocating tester producing a larger discrimination between fuels with different lubricities compared with the HFRR. It's perhaps worth noting that in a sliding Hertzian point contact test, most of the wear, or plastic deformation, occurs at the very beginning of the test. Once the difference in wear between candidate samples has been established, the number of cycles over which the test is run is somewhat arbitrary. ASTM D6079 gives a reproducibility figure of 80 microns as the approximately 95% confidence level. Plotting the average wear scar measurements for tests of different duration indicate that most of the measurements fall within the reproducibility limit, indicating that once the initial wear has taken place, further cycles result in very limited additional wear. An acceptable result can be achieved within the limits of the standard running a mechanically oscillated test for the required time at any frequency from 20 to 50 Hertz. Now, let's move on to force measuring systems. All force measuring systems have a natural frequency, giving rise to resonance, and resonance causes a measurement error. Depending on excitation frequency, the resonance error may be amplified or attenuated. Natural frequency is the frequency at which a system will vibrate after an initial disturbance. It is determined by the system's physical properties such as mass and stiffness. Resonant frequency is the frequency at which a system will vibrate with the largest amplitude when an external force is applied. When the frequency of the external force matches the system's natural frequency, resonance occurs, leading to a large amplitude of vibration. Any force measuring system connected to a known mass, such as a specimen assembly, not only measures some externally applied force, such as load or friction, but will also act as an accelerometer, so will sense any externally excited vibration. An oscillating force applied at the resonant frequency of a dynamic system will cause the system to oscillate at a much higher amplitude than when the same force is applied at a non-resonant frequency. The transfer function of a measuring system is the ratio of the output of the system to the input of the system. The transfer functions of measuring systems for load or friction in a tribological experiment are rarely analysed or specified. The closer the excitation frequency gets to the natural frequency, the greater the measurement error, with the output signal considerably amplified with respect to the input signal. As the excitation frequency exceeds the natural frequency, the amplification progressively declines until the excitation frequency equals the natural frequency times √2. At this point, the output signal becomes progressively more attenuated. The disheartening thing about this is that we can only have absolute confidence that our dynamic force measurement is free of errors due to resonance at excitation frequencies of 0 and natural frequency times √2. It is generally accepted that to keep measurement errors low, a force measuring system should not be used at frequencies above about 0.3 of its resonant frequency. It is standard practice to apply input filtering to limit the signal bandwidth accordingly. It's worth noting that damping has two effects on the system. It reduces the amplitude of the resonance, but it also reduces the natural frequency of the system. The graph here shows an unfiltered friction signal from a standard T77 high frequency friction machine running at 15 Hz and 15 mm stroke. The transition from static friction to dynamic friction at the beginning of each stroke and the resulting resonance is apparent in all unfiltered reciprocating tribometer friction force measurements, assuming that the measuring system has sufficient signal bandwidth. Whereas the initial peak signal at the start of the stroke may indicate the limiting static friction, the subsequent oscillating spikes are not friction effects. The signal perturbation cannot be anything other than a resonant harmonic force giving rise to oscillation. The reversal of the friction at the beginning of the stroke effectively plucks the force measuring system, rather like plucking a string. The magnitude of the resulting oscillations is of course a function of the magnitude of the plucking force. The rate of decay of the resulting vibration signal is a function of the inertia of the sample assembly, the stiffness of the transducer, both of which tend to be constant, and the variable damping coefficient of the system, which is a function of the friction in the tribo contact. Here is an unfiltered friction trace from an SRV3 showing similar behaviour. Confirmation of this resonance effect and measurement of the test assembly's natural frequency can be demonstrated by a simple experiment: the system response to a step change input. A mass is attached to the transducer assembly by means of a string and pulley arrangement. Cutting the string imposes a step change in force input. This is normally done without specimens in contact. You can, however, repeat the experiment with the specimens in contact to explore the damping effect of friction on the system response. We can, if we feel so inclined, directly compare the response of two different machines to the same input with the setup shown here. Here are comparative results for a T77, an SRV3 and a UMT, showing the response and resonant frequencies of the three different measuring systems. The UMT has a much lower resonant frequency than either the T77 or the SRV. This is because the device has a relatively high mass specimen assembly cantilevered off a relatively low stiffness force transducer. The SRV3 has the highest natural frequency because the specimen is attached directly to a very high stiffness piezo transducer. We can tidy up a signal by applying filtering. This effectively limits the signal bandwidth of the measuring system, removing the higher frequency components we wish to hide. Having discussed the response of our force transducers and how we might clean up the signal, it is probably worth mentioning something about sampling rate and the possibility of aliasing. If we are going to use filters, the same characteristic filter should be used on all measurement channels, especially in high frequency systems, to ensure that the information from different channels can be directly correlated and are not subject to differing time delays. When sampling the signals processed by a filter, it's important to sample at a high enough rate to preserve the information in the original signal. The Nyquist sampling theory indicates that the minimum acceptable sampling rate is twice the maximum frequency of interest. The measured amplitudes of signals at half the sampling rate are attenuated to 64% of their true value. Estimating the gain bandwidth product, an estimate of the information carrying ability of the system, shows that once an adequate sampling rate has been chosen, sampling faster than that may produce more data but not more information. The sampling rate of the system should be well matched to the signal bandwidth to preserve information content. Aliasing occurs when the sampling rate is too low for the frequency response of the system. As a simple example of aliasing, consider sampling the levels of illumination by looking out of the window at the same time just once per day. If the observations were always made at midnight, the collected data would imply that it was always dark outside. If the observations were always made at midday, the collected data would imply that it was always light outside. Now, assuming there are 12 hours of darkness and 12 hours of light, consider the effect of taking 3 samples per day at 8-hour intervals. The observations would indicate twice as much light as dark, or vice versa. As the signal is varying twice per day, from day to night, the absolute minimum sampling rate to avoid aliasing would be 4 equispaced observations per day. In practice, a bit more than 4 samples per day would be a safer option, so a bit more than the Nyquist theory suggests. How often is published friction data supported by any form of meaningful analysis of measuring system bandwidth, filtering, and sampling rate? It's important not to confuse resonance with stick slip. The former is essentially a symmetrical waveform, whereas stick slip is not. We can promote stick slip behavior by including a degree of compliance in our system. This emphasizes the deflection during the stick phase and the rapid decrease in friction during the slip phase. We end up with a sawtooth, not a symmetrical waveform. This is a nice example of altering the system response by altering the stiffness in the friction plane. It will be apparent that for a given true force input, the measured output value will depend on the properties of the complete measurement system. Having given numerous examples of test system response based on simple demonstration experiments and analysis of published data, we can now give some thought as to how we might model the dynamic response of our test systems. The table here outlines some of the parameters that we might wish to include in our models. Let's start with loading systems. This is a potential model for a deadweight loading system with vertical excitation generated by the contact. The associated free body diagram is given on the right, from which we can derive the equations as shown. This is a general model of a pneumatic loading system with vertical excitation generated once again by the tribological contact. In practice, non-velocity dependent damping may come from friction in the cylinder piston rings, with the compressed air acting as a spring. This is what a compressed spring type loading mechanism might look like. Let's now consider what the friction measuring systems might look like. This model assumes that friction in a rotary tribometer is measured at the pin and not with an inline torque transducer. That would be a different model. System excitation, FC, is the time-dependent friction generated in the contact. This is a typical arrangement for sensing friction in reciprocating tribometers, along with its free body diagram. It's important to note that in the friction plane, the contact friction affects the damping coefficient. Hence, the damping coefficient is a function of the friction in the contact. We saw this illustrated in the earlier practical experiments. Unlike the friction and loading systems, the elements of the motor drive system are not tethered to a fixed point. There are 2 mechanisms for exciting torsional vibration: periodic fluctuations in motor torque and fluctuations in frictional response of the tribo contact. The latter could be caused either by actual tribological effects or by fluctuations in load caused by the loading system dynamics. Let's now consider a reciprocating electromagnetic drive. In the case of a voice call actuator, VCA system, the moving component, hence the moving specimen, is not rigidly tethered to a fixed point, but is supported on flexural elements and electromagnetically coupled to the fixed component. The output of a VCA varies significantly with resisting force, and performance is governed by a balance of forces and electrical properties, with the constant Lorentz force it produces being counteracted by the resisting friction force. In a closed-loop system, a resisting force will affect the actuator's velocity and position. When a resisting force is applied, it will slow the actuator down, resulting in a reduction in back EMF. To compensate, a controller must increase the electrical current to generate more force to overcome frictional resistance. An increase in current leads to an increase in force. The motion equations are as shown in the slide. F total is the net force available for acceleration or deceleration. This means that for the same applied current, a higher friction force will result in lower acceleration. Conversely, for the same desired motion, a higher friction force requires a higher current. It follows that the stiffness of the driving system increases with resisting force because EMF increases with resisting force. The interaction between the VCA and the resisting force determines the overall system dynamics. This helps to explain the behavior described in our earlier experimental analysis. Mechanical drive systems are essentially tethered displacement generators and are usually designed with sufficient inertia in the form of a flywheel not to be susceptible to variations in resisting force. Combining the three elements, the loading system, the friction measuring system and the driving system, can result in systems as illustrated in the slide, the dynamic response of which will depend on the mechanical characteristics of each element and the three sources of perturbation, noting that the latter are not independent variables. This is how reciprocating tribometers might be modelled. Load and force measuring systems are usually decoupled with these machines, and low inertia, heavily damped loading systems are preferred. Dead weight loading systems can only sensibly be used at low reciprocating frequencies. Having defined our model test systems with the necessary mechanical information regarding mass, stiffness, inertia, etc., we could in theory produce a finite element model of our test system. We have, however, managed to avoid one key requirement: the thorny subject of the constitutive relationship between load and friction, and the constitutive relationship between friction and sliding velocity. It will be apparent that tribode contacts in general, even with significant stiffness in the friction plane, are likely to be subject to small amplitude vibrations. These may not only affect the frictional response, but may also affect the dynamic load. We know the limitations of the Amundsen-Coulomb laws of friction. In view of the dynamics of our diverse test systems, how far can we progress without replacing Coulomb's law with some form of rate and state friction model? It's clear that with both a tribode contact and a tribode test system, we are dealing with systems with internal feedback. This schematic shows a possible feedback mechanism for a friction-aware coupled test system. A rate and state friction model describes friction as dependent on the instantaneous slip rate and a state variable representing the changing morphology of the contact. The model comprises two equations. One for the friction coefficient, which includes direct, that's velocity dependent, and evolution, state dependent effects, and the second for the evolution of the state variable itself, which clearly must vary with wear and temperature. Of course, it may just be that the concept of state variable is just a more complicated way of saying that the surfaces in our experiment wear, and as a result, so the frictional response changes. In practice, we don't really know how and why friction varies. Topography, damage, surface chemistry, development of interfacial layers, whatever. We can, however, assume that changes in surface topography will translate into excitation normal to the surface, hence in the loading axis. Of course, when it comes to wear, we have empirical understanding, but no constitutive equations at all. Without viable constitutive equations for friction and wear, our modelling exercise comes to an abrupt halt. Thinking about the dynamics, stiffness and inertia affect both system friction and wear response. In the case of load application, higher stiffness and inertia typically gives rise to higher wear rates, including fatigue-induced wear mechanisms such as rolling contact fatigue. This is because higher stiffness and inertia give rise to higher dynamic contact pressures. Lower stiffness and inertia systems, rather like a well-designed suspension system, reduce the potential for generating high dynamic loads. When it comes to friction, the mass of the specimen carrier and the stiffness of the measuring system both affect the frictional response of the tribo contact, with higher mass and lower stiffness potentially resulting in friction-induced vibration, stick slip, and other forms of instability. We cannot, of course, afford to ignore force measurement, system bandwidth, and signal processing. Thinking about system feedback, it seems potentially attractive to treat the system dynamics in the loading axis and the friction plane as mutually independent. However, this is clearly unrealistic because frictional response is dependent on load. We have a friction and wear coupled system. There is an internal feedback mechanism comprising both the tribo contact itself and the overall machine dynamics. We're dealing with a closed loop, not an open loop system. It follows that if the feedback loops are negative in nature, the response will be to damp outputs and prevent change, whereas if the feedback loops are positive, the tendency will be to amplify outputs, giving rise to instability. How we should compare data generated by one test machine with that generated by another nominally similar device is moot. Our problems are further exacerbated by designing experiments based on inadequate friction laws and practically non-existent wear laws. The challenge can be summed up very simply. We specify the test conditions for our experiment, but make no reference to the system response of our tribometer. Yet it's the system response that we are recording. Logically, if we are to compare results from different tribometers, we need to start by comparing the response of said tribometers. If we do not do this, our diverse tribometers run the risk of becoming random result generators. We need to understand the spread of results in terms of friction and wear as a function of system dynamics, and then perhaps work out when to be worried about comparing data from different devices and when we can just be relaxed about it. It follows that data sets must be curated on the basis of system response and system bias, as well as test procedure, before ever attempting any big data analysis of published results. These issues have significant implications for the validity of big data analysis and the application of AI to tribology. So there we have it. All that's left for me to do is to thank some old friends for reading through some of my work, providing me with useful comments and information, and to thank two younger members who joined Phoenix Tribology for a short time in the summer of 2025 and took an interest in what I was doing and made some very useful and helpful comments. If you feel the need to communicate with me on the subject of this talk, you can send me a message at info@phoenixtribology.com.